got your collector, your emitter, and your base. And this would be kind of like a NPN, I guess you'd say. And the idea behind it, if we were going to draw it that way, is if my little tiny person, see how small he is there? He's just a little guy. He's not strong enough to move that big valve. But he can move that tiny little valve, and if the pressure difference between our base and our emitter is ever higher pressure here, so if he opens that valve and we have some water trickling through, it's going to push on the little hinge, which will swing it open so the water goes through, but the top of the hinge is connected to, a chain, which will open the big one and allow big volumes of water through. So they had a different illustration on our PowerPoint when we covered it, but that's basically our transistor, right? Is amperage can only travel that direction, and this diode controls the flow through that one. So, and we could put a load in here and do some work. But anyway, just a little review, if you're still with me on that. I drew in here two different transistors wired in a system. Here's how they would be drawn. It gets a little bit tricky. A lot of times on paper, they'll swing the emitter over to the other side on that one. So you just got to watch close. We're always looking at the voltage difference between the base and the emitter to decide, is the transistor going to turn on and function? So that's why they'll do that sometimes. But this one here, if we have a positive voltage and we raise it high enough between my base and my emitter, it will open up and we can feed it. So this is a version of what we got here. I probably could have put my big water load in there if I wanted instead of in there. But that's the thing with transistors, is you can load them any different way you want. So is this a NPN or a PNP? NPN, that's right. Because we want a positive on our base to open it up. So which one of these two is a NPN? We have a short delay. How many think it's the top one? How many think it's the bottom one? Yeah. So it is going to be this one, NPN. We're always looking base to emitter, and we got our little arrow pointing right, and I'm a conventional guy, so we're always going to follow the arrows the right way. So as long, it's going to want power flowing that way, and the only way it's going to do that is if we're positive and negative with our anode cathode in there. Negative side's always the little line that the arrow is pointed at. So that's an NPN. We know that's got to flow that way. That would make that a PNP. With our base and our emitter, we're going to want more positive here if it's flowing this way. So that would make this one the negative, if you will. So positive, negative. And the C is the, collector is why I had those. Collector, base. So yeah, the would be positive. So I drew this one up just for the fun of it up here. Here is a, did I draw that up? I feel like I drew that up wrong. Positive to my emitter. I would let that out. It's not necessarily that it's positive at that one. When we turn it on, it's positive. But this is one way you could draw a PNP, because my E is more positive than my base in this, or my base is more negative, I guess you'd say, PNP. So that's one way you could draw it. If we were to open this, it also allows flow through that one. But there's a bazillion different ways to do them. I don't want to get too far off in the woods with that, because you can do it a bunch of different ways. But as long as you kind of have this concept, and if it's NPN, the base has to be more positive than the emitter. If it's PNP, the base would be more negative than the emitter. That's the part you got to remember.
So like in the NPN, the E would be more negative, the B would be more positive, the C would be what?
Right. So you can wire them different ways. What we care about for opening or closing is the relationship between those two. This one is just going to allow the larger valve to be open or close. So the way you'd write it is if B is less than E, open. That's, if you're going to write it in English, that's how you'd phrase it. So that's why, and you could go review, there's a ton of different ways. Where am I going to put the load? Where am I going to put stuff? But that's really what we want to know on how they work. Beyond that, we're into engineering the chart. All right, I'm going to erase that one. Like I said, I don't believe it shows up on the midterm, but I just wanted to hit it one more time because it's been so long since we've talked about that. Yeah.
How do you know the difference between NPN and PNP?
So they'll tell you when you look up the part number on it, because you can't necessarily physically tell. Otherwise, if you have a drawing like this, where it's got the diode in there, the arrow on the diode is the anode side, or it's going to tell you the way in conventional flow electricity goes. So if the arrow is pointing towards the base, that's going to tell us that it's going to be an N, because I'm going to have more positive to push the direction of the arrow. So if the arrow is pointing towards the base, you could say N. I guess the other way to say it would be if the negative dash is on the base side, the middle number is going to be N. So that'd be another way to phrase it. If the positive, so the positive connects to the back of the arrow. So on this one, see, you got the arrow, so the P would connect to the back of the arrow.
How would you check that with a multimeter?
You know, somebody always asks those questions. When you're like, just barely know enough to teach the class, somebody goes, how would you check that?
Put your diode there.
You could put it in diode mode on your multimeter. Let's make sure this works. Double check my logic here. Well, you're going to put your multimeter in diode mode, and you're going to go across your base and your emitter. So if I go this way with, I got to get a positive lead, don't I, for this to actually make sense. Okay, positive lead, negative lead. If I were to go across that one, let me clean it up so you guys can all see what we got a little better. There. If I go like this and it works, that means I have a NPN because my positive, the diode's going to allow power to go through. If I go like this and it doesn't work, still NPN, but down on this one, it would work again, right? Because my positive pressure is just going to push through that diode. So that's how you check it. Oh boy, that was close. Almost got run over by that one. Anybody else?
Can you do the same thing with an ohm meter?
So, gets tricky. Digital ohm meters, they got logic in them, they don't like it. If you're gonna use old school ohm meters, they have a battery and a needle, you can kind of do that, but you're looking for changes in needle and it gets complicated. So you really wanna have a diode checker. The reason for that is when you put your diode checker on there, let's say we would just have just a straight diode. If we have just a straight diode like that, like in your alternators, positive, negative lead, if I put it on here, is my meter going to work? Is it going to read a number right now? Yes, because my positive is on the positive side. And I believe, and it's going to depend on the meter you have, I believe if it read 500, might read 0.5. I believe what it then reads is it's saying, hey, I've got to raise the voltage to whatever number it reads on there in order for the diode to get open. How far open to forward bias this diode? because they're never zero resistance, like completely zero. There's that forward biasing voltage. So when it reads 500, I'm pretty sure they're putting a decimal in front and you're at 0.5, right, 0.005 volts. They're putting a decimal way out here. Or you could say 500 millivolts, right? I think that's what your meter's doing when it gives you a number reading a diode. Dean would be a better guy to ask that on. So that's what we're doing if we do it on here. We get a reading, it'll be 500 or so. If I reverse it, we don't get anything. So that's what I'm doing across this diode here when I'm doing that.
And so the difference in ohms isn't, there's no difference in ohms?
It's not ohms, because what your voltmeter does is it puts a voltage in, but it's gonna like slowly raise the voltage. And once it gets to the point that it says, hey, this is enough, it starts just passing the current through. So it's not gonna hold as steady on your ohm meter. It's gonna confuse it. You're back into how the circuit board on your ohm meter works. We're gonna leave it at that. And, yeah, we'll talk in person otherwise. Okay. Any other questions? Okay, let me erase that. It's kind of like when you have a capacitor. If you're really good with an ohm meter, you can kind of tell if your capacitor is good. Because when you first put your ohm meter on a capacitor, it'll take the current until it's totally charged up, right? So it'll be like no resistance. But then as the capacitor charges, it slows down the amperage going to it until the capacitor is fully charged. And then it'll say infinite resistance. So you can go to a capacitor and you'll see it go from no resistance and it should slowly climb to infinite. But depending on who made the capacitor and how their circuit board works, if you get into a solid state one, that doesn't always work correctly. Oh, I was gonna grab, just remind me, I'll grab later, the extras list, which some of you are gonna be getting kind of close to doing. I threw on the bottom of the extras list. It'd be really cool if we had a mock-up of the starter system. Now, I probably wouldn't do the igniters, maybe we'd add that in a year or two, but in the box, I found a little on-off switch, and all it is normally open for the on switch. If I push it, it closes, but as soon as I release it, it goes back to open. And the off switch is the reverse. It's normally closed, but when I push it, it opens. But as soon as I release it, it goes back to close. So I found that switch and I'm like, wow, that's kind of cool. And then my mind pretty quickly went to, hey, could we make a mock-up so that it's not just on paper when we're doing this wiring diagram? I pulled out our best one and was looking at it. Here it comes. Was looking at it and determined, oh, I cannot use, hold on, that's bad. I cannot use that switch for this one because the stop function on here, if you remember, is electrically we actually close the switch and here it is. We actually close the switch and send power up to there. So I couldn't use that switch on this diagram, but if we went back to the old diagram, is that the old one? That's not the old one. Oh boy, it's gonna be small. Zoom in. If we went back to the old diagram, and you may need a better drawing for that, what they did was we only have the start switch connected as it's normally open. When we touch it, it's a momentary. And the emergency stop is a normally closed switch that when you bump it, it opens it up. So, I'm not saying you even if you wanna take on this project, I'm not saying you have to build the whole thing, but there's a question on, could we come up with a wiring diagram that we could make one of these? An actual undercurrent relay is quite expensive, and it's gonna be tuned precisely to your motor and all that. And my question is, we've got some gyros and stuff that take a while to spin up, so they'd go. Once they're spun up, the amp draw would lower on them. So step one would be grab one of our gyros and see what the amp draw does and if it stabilizes. And then step two would be, could we get a relay that would be closed when it's spinning but opens when it spins up? That'd be fun to make. If not, we could always just manually put a switch in a wiring diagram that simulates it. But if you wanted a challenge to play with electrical, it would actually be really good for your, I'm gonna call it your brain, your understanding of that specific wiring diagram, to kind of think through, hey, could I build this? And you could have me and Dean help and talk through stuff. So anyway, that's one of the extras when you get that far, if you get that far. I went in when I was looking for Tim Peak and for all you guys. I went into Cessna's 172 electrical diagram, so like the 172S model, 97 and on, and found a few things in here. If I look at number 5, it might be hard for you guys to read. It's pretty clear that it says wires and cables shall be positioned or protected to avoid contact with rough or irregular surfaces and sharp edges. So like going up the tail of the 182 out there, right? Now this is not that airplane, but this is in the manual for the 172. All wiring protected from chafing by use of grommets, protective sleeves by proper support, correct wiring, avoid contact with moving parts, obviously. Wiring around sharp edges should be avoided at all times. So, especially if you were in a 172S, yeah, there's no way we're gonna run that wire up through the tail. And I just wanted to kind of point this out, and on that list is to grab this and read through it when you get a chance, because it gives you some good info. Good chance in your future, you'll end up working on S models. And if you're working on an S model on the electrical, you're required to know this, which is scary, right? Like, really? Did I read that when I was in school? Well, before you work on the airplane, you better sit down and do some reading, or know it ahead of time. So just point out some of those. I thought 8 was interesting. The securing of wire groups, bundles, sleeves, adapters, clamps, and tape shall be accomplished with a clove hitch knot secured with a square knot. They give you the picture. So, you know, sometimes I get the question on if you're just tying. Do I have to do exactly the right knot? Most of the time the answer is no, just do whatever is secure. And I thought it was interesting coming through here. I'm like, whoa, they spell out pretty specifically. Now, is a DME or an actual inspector going to care if you did a clove hitch or if you did 2 square knots? Are they going to know even the difference? Probably not. But they even go to that length to spell out, yup, when you secure it, use a clove hitch. So I thought that was kind of interesting as you read through.
So if I get lacing as a practical, I could just do just a normal knot and call it a day.
Lacing is where it runs down. If you get tying, so the question is, hey, how do I want to do this? Would you want to risk failing your practical? I'd probably do the clove one. And I would say practice it so that it just comes natural. That's what I'm doing. If you're working on an airplane, let's say you're working on a Piper.
Good dive. Very good Piper product.
We're after securing our wire, right? AC-43 gives you suggested ways to do it, but we're just securing it. And my next point comes up to that. Number 12 on here says, wiring shall be supported at intervals not more than 12 inches, except when contained in ducts and conduits. Thought that was interesting, because AC-43 gives us, I believe, 24 inches, right? So Cessna on the 172S said, no, we're going all the way back to 12 inches. I was like, oh, okay. Tie wraps shall be used to maintain a bundle at intervals. Wait, what? So actually tie wraps, but no more than 6 inches or less than 4 inches. So they want you maintaining, the way they use the word, they want you maintaining the bundle so that it's not crazy hair. Corbin knows what that's like, right? You got maintained into a nice ponytail or out like crazy. So they actually tell you, yeah, go ahead to maintain your bundles, but they go a little bit further. They go, well, lacing would be the same idea, but hard, you have to look if they spell it out. Wiring supporting devices shall be of such that the wires will be held securely in place without damage to the insulation. Where was the spot? There was one more comment. 12. Oh, shoot. I didn't write down on my notes. There's one spot that says wires should not be, there we are. Tying cord shall not be used for support of the bundle. So, some of you guys, like on the 182, we put a clamp in and then we use the tying cord to support it. Well, if we did that on a 172S, we would not be compliant with their manual. So there are some interesting questions there on, oh man, should we ever use lacing knots to support a bundle or move it? The way I read this is they pretty much spell out pretty specifically, look, we're using official clamps to support our wires, and then we're going to use zip ties, cables, lacing to maintain the bundle. That's how they write it. That's what you're going to find mostly. What's interesting is they use the word lacing or tying. They didn't use zip tie. They didn't use cabling. So you're like, well, can I use cabling to support the bundle? Can I use So back to that gray area. I don't think you can. AC 43 says depending on what area you're in, but it gets foggy. So all that for just some review, and I highly recommend reading through that when you get a chance. All right, we already went over the picture here, but there is drawn out a NPN and a PNP. So here's one way to do a PNP. Positive comes in the emitter, out the base. That's just our control, it's the small valve. And what they have drawn is your positive would, in this case, flow all the way through and back out. I don't know if I like that one, but that's one way to do it. That's what we had when we studied it in airframe. So a lot of different ways to do it. If you want to go back, I threw that on there. All right. Have you guys learned yet that when you see a slide like this with blue boxes, what does that usually mean? I probably stole it from the exam. So now I will say, I purposely tried to confuse you. Now, if I say it out loud and tell you I purposely tried to confuse you, I'm not actually trying to confuse you. I'm just trying to make you think. Don't just latch on to, hey, which ones have red, or the one on the left, or the one on the right, because I did some playing around with mirror images and stuff. So you'll see these a couple different ways on midterms and finals. So my question is, which of these is wired up the way we would have it on a normal 3-contact regulator where the field, I before E, okay, gets grounded? And I'm gonna draw a name, but if you want to pass, you can pass. Let's see. Can't remember which way I'm going anymore. Isaac, did you just answer a question? Okay. You're up. What do you think, Isaac? Which ones are normal generator where the field gets grounded when we want? I'll add one more. Field gets grounded for full output. A or B? And here's what I'll do. If you pass, we're not going to let you off totally scotch-free. Label one of my terminals for me. I'll put it that way. One of my blue boxes at the top. answer A, he says. All right, so if we look at A, the key on these is where's the ground connected, by the way. So that terminal would be ground here. So that would make this positive voltage coming in. So my positive would come in through my armature to ground, except we're a generator, so technically it's going that way, but we get the idea. All right, that means my positive is going to be going through my field, around through my other field. It's not connected to ground anywhere, so yep, sure enough, this guy is going to be looking for a ground connection to make voltage. Good job, Isaac. Well done. So, you will have access to this once our lecture's done, to look through, this one. This guy, when you're looking at him, still got a ground here, and we go, ooh, one side of my field's connected to ground already, which means if I want any electricity to flow through my field windings, one side's already connected to ground, I'm going to have to connect a positive voltage out there. That would make the statement that I asked incorrect. So that one would look more like a alternator regulator, or if you guys are super sharp, it would make it look more like, I think Yoder said this the other day. I put it up on the camera. Or it would look more like your starter generator is a positive field as well. At least the wiring diagram we gave you. All right, making sense? Questions on that? Cool. I went in and tried to salvage this image, somehow turned it to gray. Just to go back to, hey, what's a carbon stack? And as a reminder, our carbon stacks allow electricity to go through if we squeeze them really tight. That's the idea. It's kind of like your brushes. If they're touching good, you have a good connection. If they get all loose, doesn't allow much through. So I had to go in and I labeled this as positive to make it like our normal generator. And I labeled this one up here ground. So the question is, how do I connect these two wires to finish my picture and make this work? Does anybody want to volunteer and try it? If not, I'll do it. Any volunteers? I should have brought you handy. What?
You got it.
For a mini Snickers.
Wait, what do you gotta do?
You got to connect these two wires to something wherever they got to go in order to make our voltage regulator work. Shouldn't be too hard. So if we look at it, if I've got positive here, these are my brushes, is why they're funny, right? So I got positive here, so positive through my armature out to ground. And we even gave you this picture, right? Positive through the armature out to ground.
Where's the battery?
Positive.
Can I just just throw something at it?
You want to try it?
I don't know.
Hey, while he's trying, I'll grab the Snickers. We'll see if he's right.
That's positive, so that's.
I'll give you that.
Put positive on the battery, yep.
Wait, so basically, if we did one of these, and then one of them,
Let me grab your candy and see if you're right.
I don't think that's right.
You gotta remember how to draw voltage regulator.
Wait, I gotta draw one? Is that what's covered up right here?
Yeah, you gotta draw what's covered up.
I have to draw what's covered up? I'm
You
confused.
just gotta fix it. I covered stuff up because it wasn't ground. The picture didn't work. So you just ignore the boxes. Okay.
When we think about it, that kind of makes sense.
So you like it like that?
I don't know.
Have a seat so we can all see what you did.
That means I got it wrong.
I'm a good throw. I even gave you this picture to hopefully help. So we already said if we were going to draw our wires, this one that goes from arm through my armature to ground, we go, okay, well that's easy. Positive through my armature to ground. So you all see that wire, right? Good, tracking. So now we need to say, okay, well what goes through our field on this? From arm through my field out to my voltage thing. So from arm through my field out through my voltage regulator. And we said that's gonna go out to ground, right? So out through my voltage regulator to ground, so we got it, you nailed that part. So then how the voltage regulator functions is when we have a high voltage, we want it to say, whoa, 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 that's too much, right? So we want this to energize when the voltage is high. So we're already connected to ground on one side, so we're just gonna put our positive that this thing's making, and when the voltage gets up to, let's say it's a 24 volt system, if that voltage gets up to 27 volts, this guy's pulling really hard, makes our carbon stack loose, and is gonna kill our ground connection. So that looks great, Kuvar. Nice work, man. Alright,
It was so worth it.
cool. Very good. So that's how we used to do voltage regulators. The issue with that is this isn't protecting from back current, right? That's not protecting from reverse current, and it's not protecting from over amperage. All it's doing is the voltage regulation. We said, well, we need more stuff than that. So that's why we went to our 3-contact voltage regulator. That's what I'm calling these things. Somebody might have a different name for them, but that's what helps me. 3-contact vibrating voltage regulator. And remember, sometimes they're laid out where we got voltage, over current and reverse. That one's reverse current. Sometimes they're flipped the other way on there, so it's all depending on how the manufacturer decides to lay it out and wire it. That image didn't go real well. We covered this a little bit yesterday, but basically if we're tracing our power through from our field, so we've got positive goes through one field, through the other field, it's looking for ground. It's going to go through a normally closed contact on our over voltage. It's going to go through a normally closed contact on our over amperage. Well, something went wrong with that picture. Did something go wrong with that picture?
Somehow the current's gotta flow through your
Yeah,
spring, your coil, right?
hold on. Where'd that picture come from? That's a bad picture. I gotta get rid of that picture. Let me go to the next one. Wonder how that snuck in there. Weird. Now it's the same picture that moved. We'll draw our own. We'll draw our own and we'll fix that later. Alright, so this is back to our memory. John, you got it figured out, right? So we do know our field, here we'll draw it. There we go. So we do know it's going to go through 2 normally closed contacts. What are those going to be labeled if we want to label them?
Voltage over.
Over voltage and over, I'll put amperage. Okay?
That one's reverse.
And the last one out here would be reverse current.
Is that worth a Snickers?
Not quite. So we're just going to go through those 2 down to ground. So everybody tracking with me so far on that one? What we're doing? We don't have anything wrong yet. Apparently that last picture, I don't know how she got in there, last year's drawing. Alright, so what are we missing in here so far? I don't have a coil for my over voltage. I don't have a coil for my over amperage yet, right? So we're going to take all of our amperage out of this thing. We'll jump them. That would be my A terminal, right? Coming to my arm. So we're going to take all of that and we're going to run it through my coil for that one. And then we're going to run him through my reverse and out to my battery. Everybody tracking us so far? Did we mess anything up? Cool. So that's our fat man. So we need a little man to close first, and oh good, that blue line is positive voltage, right, coming off. So we can jump off. Now different brands do it different ways. I've seen them take it off right there. I've also seen them, I think most of them will take it off. It's still positive voltage on that far side. Remember, there's some resistors and stuff they do in there so our contacts don't burn. But basically, we'll take that positive voltage and we'll make wimpy, and he just goes to ground. And we'll take that same positive voltage, can I sneak through there without getting in trouble? I should have went the other way. We'll go above him. Go from that one to ground. So if my positive voltage gets too high, it's going to open my normally closed. My amperage gets too high, it'll open my normally closed amperage. And this is normally open, so on that one, basically we have to establish at least some voltage, enough for Wimpy Man to say, okay, click, oh. I didn't run. Somebody's got to run through there. Is it going to be this guy? That looks better. All right, so wimpy guy, yeah, that looks better. This one might hook up here.
That's what I thought, otherwise reverse current.
There. So, once wimpy closes this, he goes, okay, let's make some power. We're sending power to our battery, but if my generator slows down enough that my battery is now stronger than my generator and current starts flowing back through that one, now Fat Man says, I see you're trying to hold me closed, Wimpy, but I'm stronger than you, and he'll pop that open, and once that's popped open, now we don't have any amperage until this ramps up again. So, back to just kind of working through like we did there. It'd be good to have that much understanding of what's going on. Now, the reality of things is, we're not using these on much anymore. We're going to use solid state. That's why we kind of started off with that transistor slide.
What was the trick again in knowing what the difference was on the regulator itself?
On the
Small windings, was that the
yeah,
one?
so when you're looking at these, the one that's all tiny little windings is going to be the over voltage relay. So over voltage has all small ones. The middle one, to my knowledge, is pretty much always over amperage. So the other trick would be whatever two are connected together, see how these are connected? That's going to be your ground points. They happen, on this one, the points are, I think they're up under here. Those are your ground points. So you know one's going to be over voltage, one's going to be over amperage on the ones that are connected. So if this showed up and the two were over here, you'd go, oh, they're switching stuff around on me. The other trick is, a lot of times Fat Man will be wound on top of the skinny guy underneath there. So, yeah. All right. We are going to take a little break. Basically, we're just going to talk through this a little bit, ask some questions, kind of like we did with the starter generator, and that's pretty much the end of our slide. So go ahead and take a break till 12:30, and then we'll come back with some questions on this one.
I asked about the tours, they said no. I've toured some factories, but pretty cool. I've never been like
I guess it was a good thing to switch to the reverse current one, because otherwise you would have still been
fortunate.
energizing your current the same way.
It's mostly just
Yeah.
laser and plastic.
Which may or may not
Because they
I think that's gonna be the right size, so that way you could bring it up and display it.
It'll have to be smaller than the 4 then,
Well,
Keep going up by
like 1.5 or so.
seconds a week,
I might work on
minute
that.
a month.
'Cause the longer that back leg is, the more stable when you're.
I mean,
Last
we
week's
have a
was
lot of
that
that still.
Okay.
Graduation really long, but they're really super heavy,
And to carry around would be,
and it's already super heavy.
that's part of why I was like, if we had one, you could just slide it in when you crank
You
it.
could, if you take the angle iron and set it on top of the weights that are already there, you could run bolts through. Or underneath. Plus, just in case.
Where are you getting the angle iron from?
It's in scrapping.
Okay. That's not a bad idea. 'Cause even if you didn't attach a pole, all you gotta do is set it on and just throw some.
Yeah, you can mag through it.
Just throw them through. Well, I just mean like, say you brought it in here. You'd set your angle iron down, set your device on it, and just throw in some long ones. All you gotta do is keep it rolling. Really, only need one to bend. It's one.
Yeah, right now it's got 2 legs, so if we put one more piece like this, then you can put a 2x4 here, and then just run a bolt into it. So then it's holding the 2x4 off. I can show you when we get out there. Okay?
Sounds good. Oh, hey. Alright, I threw up there, I know it's hard for you guys to read, but just pointing out, this is the 172S model, so 97 and on, alternator setup. So, here is our alternator, and following wires around field, it actually comes back and comes to terminal A. It's like, wait, what? Terminal A? That's not how it is on this one. So the terminal designations do change, right? So it's not a universal. That goes back to, I think, day 1 in here we said, there's no universal way of labeling wires. The idea is they pick whatever letter they want, and even Cessna changes it. So what's missing on here is the power to this one. You got ground, and then you've got low voltage to your panel. That would kind of be like the I terminal. So ground, I, field. So basically we got 2 left. One is going to sense. That would essentially be like the A coming in on the other diagram. And here is our power. And basically, where are they going with that one? Oh, up here. Power control. No? Let me turn this one on. Why am I tripping? I'm looking for my alternator switch that goes click to turn it on. And not that one. Field, not that one. Power.
Case we couldn't find it in this diagram when we were looking yesterday.
I think what they're showing is this one here comes out, and you'd have to read that. There we go. Switch panel. Circuit breaker. Huh. Well, anyway, point being, what I wanted to point out was the letters change on you. So make sure you're following the diagram for the letters where you're at. I believe it's going to be this power one, and it's just a tough diagram here where you're like, where are you guys going with this wire right here? What does that go to? You'd have to chase that down. But all right, back to what we have though, the one you're actually going to work through. Remember, these are vibrating contacts or vibrating points. We don't use these much anymore. So even with that logic, it's like, well, we could update this with the vibrating contacts. We're looking at a couple different contacts. These guys are normally open, and they close when we say, hey, start making power. And I use that phrasing to say S, if I supply power to S, I'm going to go through that little coil right there. That's going to close this set of contacts, is how that's supposed to be drawn, to say start making power. So if we supply power to that S terminal, we're telling the voltage regulator, start making power. What it will do is it'll take the electricity from that red wire that's getting it from A, and A, you could say goes back to A on the alternator, or you could say it goes, it's not gonna be load meter, goes to, where's our bus?
All the way off to the right and down.
All the way off to the right and down. All the way off to the right and down. So whether you say it's coming from the A on the alternator, or you say the alternator circuit breaker on the bus, either way, it's taking power from that A terminal or the bus, and it's gonna use that voltage to go through that set of contacts, and our ultimate goal is to get it to F. So if I trace F backwards, our ultimate goal is to go through those contacts right there to get it to F. So that is the ultimate goal of this device, is we take power from A, once the S says, yes, start making power, that closes, it goes through these contacts, out to F, to our field, to give the field a positive voltage and say, hey, give me the maximum voltage. So these ones are, you'd say, normally closed, and they would open if the power that the alternator is making gets too high. And then a quick review, it's a little bit of a funny drawing, and you're like, well, what is this then? The idea behind that one is if we ever got to where it was just jammed and the alternator's going, wah, and making way high voltage, instead of just assuming that those contacts open, because in order for it to do that, those would have had like stick or a problem, is it actually takes and it grounds out the input signal to it, and kind of says, just ground that baby out and cancel it, which would typically either pop a circuit breaker or do some other funky stuff to that method. So, A is our output on our alternator, which is connected both to the bus and to a regulator, just so it knows what voltage it's getting. F is the field voltage to say, hey, I want power. S is, on this drawing, you say start making power, closes that one. And then that leaves I. I is that indicator light. And the indicator light drawn in there, here's our light, right? Basically, in normal operation, 1/2 of this light is always gonna have positive power from our alt field circuit breaker. So it's looking for ground to light that light bulb up. So it's actually looking for a ground. So coming in through I, it says, hey, how do I get to ground? We got all these resistors in here, so if we were sitting like that, it would bleed through those resistors to ground and the light bulb would come on. So those resistors would be, I'm going to draw them, this is going to sound silly, but those resistors would be giving off a little bit of heat. We'd be giving off heat, and we would also, I'm going to draw it as giving off heat. We would also be giving off heat from our light bulb. The bulb would be burning, right? So that's how that indicator is normally designed. Now that's with that open. As soon as we close this switch by putting power to S, now what happens, don't get off my wire, is the let me erase that so it's not funny. The light bulb still has a positive coming from here, but across the light bulb, with that closed, the power can just go right to A, which A is connected back to our bus, right? So the light bulb won't have voltage across it. Now, we will still have amperage going through those resistors, and they'll be giving off heat, but it's just a little bit. So the light bulb only illuminates when this set of contacts is open, saying, hey, the only way for your power to get anywhere is you have to go through the light bulb and then through the resistor. So it's kind of a backwards way of doing it, but just so you understand what's going on with that. And if you have questions, ask me, ask Dean. But that light bulb will always have power to ground, if you would. If you were to put a voltmeter on it, voltmeter to ground, the light bulb is pretty much always going to have it unless that circuit breaker there is tripped. Am I following the right wire? Yeah, unless that circuit breaker there is tripped, it's always going to have power to ground. The reason they do that is there's a backwards method of powering as well. Question?
So what's keeping that voltage from bleeding out through the ground on this lower left cylinder or lower right cylinder?
This one here?
Yeah.
It also is, you'd say, going through there as well, because that solenoid, that's the coil
Right.
for what opens or closes our switch.
So if we're getting voltage from our light, that's connected in.
Yeah, it's bleeding through there.
So wouldn't that light always be on?
Let me draw it a different way. So if here's our light bulb, and we had a battery, and we have a plus and a minus. I hook that up to ground. All right, is my light bulb on?
Yes.
Okay. Now, just for the fun of it, if I add a resistor in there, is my light bulb on?
Yes.
Yes. What if I go like this? That's a draw a different way. Is my light bulb on?
Yes.
How about now? No, now it's not on, because this is the lowest resistance. There's no way electrons, little ants if you will, they don't want to go through that high resistance when they got a free ride through the switch. So that's what's going on inside of there, is we have that switch, that's this normally open contact, and electrically it's in the circuit like this. So if that switch is closed, there's no way we're going to light up the light bulb. So even though the light bulb, essentially, you draw the circuit breaker, essentially always has power to ground, it sometimes is not the path of least resistance, and electricity will take the path of least resistance, especially if it's zero resistance. Does that make sense? And great question. That's not normally how we simply would do a circuit, right? So, all right. All right, so if our over voltage relay were to get too high of voltage, it's going to open that, and the only way to reset it is to reduce the power coming into the inlet side of it, which basically means, if you follow the wire all the way back, you pop the alternator field circuit breaker, that turns the power off, and it goes, okay, I'll reset. Then we kick it back on. As long as it's not over voltage, it'll allow it through again. So flying airplanes that are set up this way with an over voltage relay, if it ever over voltages, the light comes on because we don't have power at S anymore, and the pilot goes, oh, I'm not making power in my alternator. And he pulls the alternator circuit breaker, pops it back in, that resets this guy, and we try again. That's how the light bulb on those are set up. It's basically just to tell you, if the light bulb comes on, you do not have power at S.
So since an alternator is engineered to just give you max voltage, when would it be over voltage?
It's not max voltage because this little dude and the contacts are at a set voltage.
But I mean, over voltage relay, when would that ever?
If this failed. So this little guy here is our vibrating contacts, our voltage relay. He's going to be set at, we'll say 14.7 volts. So that guy is going to adjust the field voltage to target 14.7. If he fails and starts to give 16 volts, then this guy goes, ooh, 16? That's too much. I'm going to open up.
So that guy is what is doing when you
Well, this is controlling the field. It's not for max output, it's looking at voltage. So your voltage regulators always look at, I wanna maintain voltage. So the contacts, vibrating contacts, is maintaining the voltage. If it were to fail and overvolt, we have a device to say, hey, let's catch that, so we don't burn our system up. The engineered to not give us more is amperage. There's a certain amperage that they won't really go over. You can't get anymore, yeah. So I think you're thinking my amperage, yep, nope, we're talking voltage. All right, I think this is the last one. So here's a Cessna 414, here's one of your midterm, I think it's midterm, at least your exam questions, straight off it with the correct answer picked for you. Man, I'm generous today. Aircraft that operate more than one generator connected to a common electrical system must be provided with. This one always, I'm tempted, I'm so tempted to do that one because there's a question similar somewhere, but they don't have to be automatic. What it is you need a switch to turn on each generator. So in this system, it's actually alternators, but on the 414, this one says left alt, this one says right alt. Can't remember what the middle one is. So basically, we've got a switch for my left alternator, I got a switch for my right alternator. Those are the switches that are individual generator switches that can be operated from the cockpit during flight. So if you read that question, you're like, what are they talking about? They're saying you can't just have one switch that you say, turn on all my alternators. Each alternator has to have its own switch, so you can turn one on, you can turn the other on, you can turn one off. So that's why I kind of gave you the image. So it goes along. Does that make sense for y'all? Okay. Every time I read that question, I go, I want to pick this one. That middle one is also tempting because it would make sense to have it do that, but it's not automatic. Often we have switches or isolation relays so that we can isolate loads, but that isolation does not have to be automatic.
Do pilots have to turn on the
Start the aircraft? Yeah. Yep. Yeah, on a Cessna 206, if you remember, we have that switch that'll say BAT and ALT. It actually looks like one switch that's split though, remember? Most pilots, they're just gonna roll their thumb across the top and kick them both on at once. So,
when did they do that?
right when I jump in, I go, is my gear down? Yep, my gear's down. All right, battery alternator coming out. So, yeah, and that's why, I don't have the picture here, but you've seen them, they're in the box, little switches, and they're practically connected to each other, so the pilot does both of them. And the idea behind that is so that he doesn't have to turn the battery on and accidentally forget, oh, whoops, the alternator. And that goes back to, there are some people that would say, turn the battery on, start the aircraft, then turn the alternator on. It's a school of thought. Dean, and I follow Dean's school of thought, is, no, let's turn the alternator on right away, because even if the engine just goes and dies, those couple the alternator will be trying to put a little bit back in our battery. The people that say you do the battery first and the alternator later, they think maybe that coffin's gonna mess with your system, but I don't agree with them, so I don't have to explain what they think. All right, that is all we got. Lab time for the rest of the day.